Hello everyone. Today I will be talking about programming challenges for heterogeneous multi-die chips. In this short presentation, I will explain what these chips are, why they matter, and some examples from the industry. First, let's understand what a die is. A die is a small block of silicon that contains the circuits of a processor like CPU cores, cache, or memory controllers. Traditionally, processors were built as a single large monolithic die, but as designs got more complex, this approach became expensive, harder to manufacture, and less power efficient. A multi-die chip solves this problem by combining several smaller dies, also called chiplets, inside a single processor package. Each die can perform a different function and together they form a complete system. Now, when these chiplets are heterogeneous, it means they are not identical. Each die is specialized for a particular task. For example, one die might be a CPU for general purpose computing, another die could be a GPU for graphics or parallel workloads. An AI accelerator die can handle machine learning tasks, and a memory die can provide faster data access. These heterogeneous dies are connected using advanced packaging technologies like 2.5D interposers, 3D stacking, or high-speed interconnects so they can work together efficiently. So, why are heterogeneous multi-die chips important? There are a few reasons. Performance. Specialized dies accelerate specific workloads like AI or graphics. Flexibility. Manufacturers can mix and match different chiplets to create new processors. Cost effectiveness. Smaller dies have higher manufacturing yield and lower cost. Scalability. It is easier to upgrade or expand by adding more chiplets. Some real-world examples include AMD EPYC processors, which combine CPU cores with an I/O die; Intel Media Lake, which integrates CPU, GPU, and AI chiplets; Apple M1 Ultra, which connects two M1 Max dies using UltraFusion. To summarize, a heterogeneous multi-die chip is a processor made up of different specialized silicon dies working together in a single package. The goal is to deliver higher performance, lower cost, and more flexibility than a single large chip. Now, let's look at the programming challenges. Programming heterogeneous multi-die chips is not straightforward because these chips combine different types of dies, each with its own architecture, memory system, and interconnect technology. For developers, this means they have to carefully manage these differences in order to achieve good performance. Without proper optimization, the chip may not deliver its full potential. There are several key programming challenges when working with heterogeneous multi-die chips. First, we have different architectures. CPUs, GPUs, and AI accelerators each need their own programming models and tools, which makes development more complicated. Second, there is the issue of data movement. Moving data between dies is slower than moving data inside a single die, and this can easily become a performance bottleneck. And third, we face interconnect limitations. Communication across dies has latency and bandwidth constraints, which developers must carefully manage. The fourth challenge is workload mapping. Decide which die should handle which task is not simple. It requires intelligent scheduling to balance performance and efficiency. Finally, there are tooling gaps. At present, debugging, profiling, and compiler support for multi-die execution now is still limited, making the developer's job even harder. To address some of these programming challenges, researchers have introduced the PASTA framework, which stands for Programming and Automation Support for Scalable Task Parallel (HLS). This framework helps make programming heterogeneous multi-die systems easier and more efficient. Some key points. It uses a task parallel model, which supports efficient programming of multi-die FPGAs by breaking work into tasks that run in parallel. It provides buffer channel APIs, which allow tasks on different dies to communicate more effectively. It offers automated compilation so developers can generate high performance hardware designs without manually writing every detail. The framework is open source, including front-end libraries, a compiler, and back-end optimization tools. And most importantly, it enables scalable performance, balancing raw speed with programming productivity. Now, let's look at some of the solutions and strategies being used to overcome these programming challenges. First, we have programming abstraction layers. For example, Intel's One API provides a unified programming model across CPUs, GPUs, and FPGAs. Similarly, AMD's ROCm offers an open ecosystem for heterogeneous computing. Second, there are advances in interconnect technologies. High bandwidth die-to-die connections like UCIe and Infinity Fabric help improve communication and memory sharing between chiplets. Third, the tooling and ecosystem are evolving. Developers now have profiling and debugging tools for heterogeneous workloads, along with portable libraries and frameworks such as SOCL, HIP, and MPI. And finally, there are best practices. Developers are encouraged to focus on portability, scalability, and performance tuning. Writing hardware agnostic code where possible makes applications more future-proof. These chips have strong real-world impact. In high-performance computing, they provide scalable performance for simulations, weather forecasting, and data analysis. In AI, specialized dies accelerate training and inference, making models faster and more efficient. And in edge computing, compact multi chips support real-time analysis in IoT, smart factories, and autonomous vehicles. They are also shaping supercomputers, helping reduce cost and interconnect bottlenecks while enabling exascale performance. Finally, in industry, major players like Intel, AMD, and Nvidia are all adopting chiplet-based designs, showing a clear trend toward heterogeneous integration for better performance and energy efficiency. To wrap up, heterogeneous multi-chips are shaping the future of high-performance computing, AI, and edge devices. Programming these chips is challenging because of their diverse architectures, communication overhead, and optimization complexity. However, tools like Cluster Framework and programming models such as OneAPI and ROCm help developers overcome these challenges. Industry adoption by Intel, AMD, and Apple shows that mastering these techniques is essential for real-world applications. Finally, ongoing research and improved tooling will continue to make programming multi-die chips more efficient and accessible. That brings me to the end of my presentation. Thank you for watching, and I hope this gave you a clear understanding of heterogeneous multi-die chips and the programming challenges involved.